All right, let me start off this class by sharing what is the end goal of this class. This is a wallet that has been created by Keshav that lets you, number one, somehow generate a wallet, generates some random, looking words over here, and generates a bunch of wallets. And you can click on this add wallet button and do more things. Very complicated stuff. But if you look at it, this is very similar to what happens in wallets like Backpack and wallets like Phantom. So what he has built by the end of it, what was supposed to be built by the end of it, what was the goal of this class was for you to be able to create your own web-based wallet. That is exactly what we will learn in this video. Even though we already covered this last week, some bits of it, we are going to cover it again from scratch. Specifically, the slides that we are covering are these slides here called public key cryptography. If you understand public key cryptography, and what is asymmetric encryption, what are public private key pairs, how can you create them, how do transactions work on the blockchain, how can you create HD wallets, then you'll be able to understand how to create a website like this. And just to give you some motivation, Keshav's website was so clean that he got hired as a designer come developer because number one, he did it very fast, number two, he did it pretty independently. Last week, we were supposed to sort of cover the whole thing. We were able to cover only until this point. He himself read until this point. He understood everything, created his own, wallet and showed. It looked so clean. Getting hired is a combination of knowing things while being very fast and also extreme amount of polishes, which he did. And he's doing fairly well. I've looked at a few of the designs that he's made. He's also coding them, even though his hired was a designer. But, he's also coding them and, making extremely clean UIs. So, just to give you some motivation, if you want to, stick through the end of the class, this is a great way to show proof of work and then eventually get hired. With that, let's get into the video. Alright, hi everyone and welcome to another video on public key cryptography. We covered this last week in a live video. We weren't able to finish it. There were a lot of questions and doubts, which is why we're going to do it again, slowly and actionably. By the end of it, completing this assignment that was mentioned over here, which requires looking at some open source code bases, nothing too complicated. But before that, let's go over everything from slide 1 to slide 8. Let's get right into it. The goal of the class was to create a simple web-based wallet. What is a web-based wallet? Well, something that looks similar to Phantom that I have over here. It shows me I have this much balance. It shows me I have this Solana address. We'll understand what this address is. But building something like this where users can come and create more wallets. For example, if I click on this top left icon, it lets me add a new wallet. I can create a new account. And now I have my third wallet. Now I have my fourth wallet, so on and so forth. I can create multiple accounts using the same private key that I have over here. Not the same private key technically, the same seed phrase. We will understand what all of this is, and then we'll try to make something similar to this on the web. When we reach the implementation phase, you will require some basic React knowledge. So feel free to take that as a black box if you don't know React yet. Let's get right into it. How do banks do authentication? This was how a bank usually does authentication, by which I mean, you go to netbanking.bank.com and you have to log in with a customer ID and a password. That's how you usually log into a banking website. And once you do, they show you your balance. They show you all the transactions that you have done recently. They also let you send this money out to other people. That's how a traditional bank does it. Do blockchains do something similar? They are similar, but what you have is not a username password, and the blockchain doesn't give this to you. You can generate this yourself. It might sound very weird, but yes, if you saw over here, when I click on the plus icon, a new wallet is created for me locally. I have not told the blockchain. I did not have to register with the blockchain. I did not have to sign any paperwork. I myself generated my own public key. What is the public key? This thing that you see at the top right here. Ignore all the other blockchains. Let's say we're just focusing on the Solana blockchain. The thing that you see over here is what's called the public key. And with every public key, there is an associated private key. Why do you need an associated private key? Because whenever you want to send money out to someone, you have to use your private key. all of these transactions can only be done using my private key. I can receive money using public key. I repeat, if I want to receive money from my friends, I can give them my public key, they can send me money. But if I want to debit my account, if I want to send out money to other people, I have to use my private key. So what have we learned? In this slide, we have learned the following: that you need a public key and a private key to be able to transact on the blockchain. As long as you have these two, you can now participate in the blockchain, send other people some Solana, some Ethereum, receive it from this public key. As the name suggests, you can make it public, which means you can share it with your friends if you want. Oh my God, that is so wrong. You can share it with your friends. You can, advertise it to the world. For example, Donald Trump has a Solana address. To keep securely with you. If you don't keep this securely with you, other people will be able to debit your account. For example, if I open Phantom over here, you can see I have a wallet in which I have $1.40. This is the public key of that wallet. If I copy it and show it to you, this is the public key of that wallet. This I can share with the world. I just shared it with you. This public key is enough for me to get my current balance as well as all the transactions that have happened. For example, if I go to solscan.io, which as the name suggests is a scanner on top of Solana, and I paste my public key, using just the public key, I was able to see I have $1.4, and these are all the transactions that I have done in the last 1 day. To be able to debit this account, to be able to send some money from it, if I want to use this send functionality, then I need my private key. This is something I should have secure with me. If I go to my settings account and click on show private key and put my password, if I share this with you, then you can debit my account. You can take this $1.40 from me, which is why, as the name itself suggests, keep this privately with you, keep this publicly with everyone. You might ask, Harkirat, this though is not private. Phantom has access to your private key. And that is true. If the folks at Phantom, want to do shady things, they can actually, take my private key and send it to their servers, which is why you should always, have these wallets that are open source and read through their open source code base. Make sure they're audited before you are using these wallets. If there's ever a bug in these wallets, then yes, you can lose your private key. And this has also happened in the past with a few wallets on Solana. I'm forgetting the name. I think it was called the Glow wallet, not the Glow wallet. One wallet was there, in a single day, $5 million were being stolen from people. And the source of it came out to be a wallet that was, insecure. That was logging the user's private keys somewhere. Cool. Question is, how can you generate a public and a private key? The next two slides are going to focus on bits and bytes and encodings. These are necessary for us to learn because private keys that you see over here and even public keys are generally encoded in a specific format. And whenever you generate them, whenever you use them / represent them as bits and bytes, which is why before we reach slide number 5, we need to understand slide 3 and 4. What are bits and bytes and what are encodings? Bits and bytes, we've discussed a few times now, but it basically is a way for you to convert, let's say, a number to binary. If I convert 1 to binary, the binary representation of it, which is its representation in bits, is 1. If I select the number as 2, its binary representation is 2, 1. If I select the number as 5 or 6, let's say, its binary representation is 1, 1, 0. Do we understand how this conversion is happening? We've discussed this in a class. Okay, when you have a binary number, the way to convert it into a decimal number is multiply the last bit by 2 raised to the power 0, that is 1. So 0 into 1 plus 1 into 2 raised to the power 1. What is 1 into 2 raised to the power 1? That is 1 into 2, which is 2. And the third bit over here, which is also 1 into 2 raised to the power 2, which is 4. So what is this binary representation converted to number? It is 2 raised to the power 2 into 1 plus 2 raised to the power 1 into 1 plus 2 raised to the power 0 into 1. This, when converted to a number, is what? 4 into 1, that is 4, plus 2 into 1, that is 2. 4 plus 2 equal to 6. This though is multiplied by, this will be 0 over here. 4 plus 2 is what converts to 6. So 6 ki binary representation is this. And if I swap them out, then 110 when converted to a decimal number is 6. This is how numbers are converted to bits. And similarly, strings can also be converted to bits. In fact, any data structure you look at eventually gets converted to bits like these when it's, fed into assembly, if you've heard of it. All high level code that you write, if you ever write, const x equal to 202, let's say, this 202 eventually gets converted to bits, and that is what is stored in memory whenever this program compiles. If you take a string, then it's slightly more complicated, but still it can be converted to bits. For example, h gets converted to this binary right here. If you take this binary and convert it to decimal, you will see it represents 104. And if you remember from the last class, we discussed something called ASCII. If you look at the ASCII representation of h actually represents 104 in ASCII, which is why if I'm taking h and converting it into binary, the binary that is generated when converted into a number is actually 104. Similarly, if I, let's say, select small a over here, the binary that it is converted to, when I convert that binary over to a number, it becomes 97. And what is 97? 97 is lowercase a in ASCII. So any string that you see, including this public key that we will see eventually, can be converted to a bunch of bits. If you take 8 of these bits together, that is what becomes a byte. I repeat, if I type HELLO, you will see this is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte, and this is 1 byte. All 5 of these are 1 byte. To store a string of 5 characters in memory, you need 5 bytes of space. And that is what, bits and bytes do. The way to represent bytes in JavaScript is using this uint8 array. That was the goal of this slide, to get you comfortable with this uint8 array. Let's write some code to get a little more comfortable with it. We have seen a bunch of these conversions on this website and this website. Let's try to write some code that lets us do the same thing. Let me go to Replit, select Node.js as my environment, click on create REPL. And let's select a string over here. Let str equal to h. What was the binary representation or h converted into bits? It was 011010000. And we said this is how much in binary? Sorry, this is how much in decimal? This is 104 in decimal. Let's write some code. New text encoder str dot encode const binary representation equal to this thing. Then let's do console.log binary representation. If I run this code over here, what has the code said? It said const binary representation. I defined a new variable, called it binary representation equal to new text encoder. What is a text encoder? It is a class. If I'm writing new in front of something, that means I'm using a class. For example, if I write let d equal to new date, then I'm initializing a new object from the date class. Similarly, here I am initializing a new object from the text encoder class. What does the text encoder class do? As the name suggests, it encodes some text, in this case h over here, into binary. And if I log the final thing, what does it say? It says this is a uint8 array. It is an array of integers, each integer being 8 bits. Whenever you define variables like these, where a equal to some big number, this is not 8 bits. This is 32 bits, 64 bits based on what machine you're on. But since in our case, we know that strings can only be converted into a byte. I repeat, a single character can only be converted into a byte. What is the maximum value of a byte? What is the maximum value a byte can have? 255. So representing this, string as a byte in a uint 8 array is much more optimal than representing it as a, simple array. I could totally do this. Okay, const binary representation 2 equal to an array which has 104 value. It's similar, right? Here also I have an array which has one value 104. Here also I have an array which has one value 104. But the difference is this takes a lot of space. This will only take up 8 bits for every element. This is a uint 8 array. This is a normal array which can be a 32-bit array or a 64-bit array based on what machine you're running this code on. So why use uint 8 array over native arrays? What are we doing here? If we use the text encoder class, it returns you the binary representation as a uint 8 array. It does not return it to you as a native array. And why is that good? Because number one, they use less space. Number two, uint 8 array enforces constraints. It makes sure every element does not exceed 255. It doesn't even have enough space to store more than 255. It only has 8 bits. So if you try to store a bigger number in there, it will not be able to. It will just round it up to between 0 and 255. If I write this code, const add equal to new uint 8 array with one value inside, which is, let's say, a very big number, and then I log array, you will see it creates a new uint 8 array, but the value in there is rounded down to 127. This bigger number cannot be stored in 8 bits. If I copy this and paste it over here, as you can see, this is more than 8 bits. 1, 2, 3, 4, 5, 6, 7, 8, and then 3 more bits towards the left. So only these last 8 bits are what gets stored and everything else gets ignored. That is good because we want to store various bytes. We want to store various 8-bit chunks together, which is why if someone gives us a very bad number that cannot fit into a byte, we will convert it into a byte. We will ignore every character after the last 8 bits over here. Cool. That is what are bits and bytes. That is how you convert a number to a bunch of bits. For example, if I type 20 over or 10 over here, this is that number converted into a bunch of bits. This is how you convert a character into a bunch of bits. If you take 8 bits together, that is what is called a byte. Usually you're converting, you're representing your private keys, public keys as an array of bytes, because that's just the most common way to represent public and private keys, is to convert it into a uint 8 array which has various bytes together. For example, if my private key, let's say, is let me copy my private key here. Let me copy this public key, const public key equal to this thing right here. And even though the code that I'm writing is wrong, I repeat, the code that I'm going to write now is not exactly correct, but you can say this public key when converted to bytes looks something like this. Const bytes equal to a new text encoder dot encode public key console.log bytes. If I run this, you see it gets converted into a bunch of bytes. This is a very long string. If I take a small string, then sure, it will just get converted into a single byte, 69. If I take E over here and paste it over here, it gets converted into this number, which is 69. So this code seems to convert a string into bytes. Now this string is not in ASCII, which is why this is wrong. You still see a bunch of bytes here, which is fine. But this string is not in ASCII. It is in something else. It is in base 58. Which is what we will learn in the next slide. We will learn about encodings in the next slide. All right. one last slide before we get into the meaty bits. Bear with me for another slide over here. It's about encodings. Usually when we're writing code, we're comfortable writing code like this: const name equal to Harkirat. But as I said, this is just ASCII, something that humans understand, some characters that we're comfortable with. For example, A to Z, let's say capital A to capital Z, 0 to 9, so on and so forth. But there are actually a lot of characters in the, not just the English language, but generally. So there are various ways you can encode, I repeat, encode a bunch of bytes. This is one way. Okay, if you have a bunch of bytes, for example, if I convert Harkirat to bytes over here, you will see this. If I have these bunch of bytes, I can convert this to Harkirat if I'm using UTF-8 encoding or ASCII encoding. Let's say, what is UTF-8 Harkirat? We will come to very soon. But I can also convert this into, if I take two of these together, let's say, okay, our first 2 bits I'm going to represent as one character. Second 2 bytes, I'm going to represent as another character. Next 2 bytes I'm going to represent as a third character. Next 2 bytes I'm going to represent as a fourth character. If I do this, then this is a different way to encode my bytes. I can encode it as Harkirat. I can encode it as this. I can maybe encode it as, I'm going to take only 4 at a time. So first 4 I'm going to represent as A. Second 4 I'm going to represent as D. Then these 4 I'm going to represent as J. These 4 I'm going to represent as P. And then, again, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this 8 bytes can actually be encoded to just 4 characters, 8 characters, 16 characters, based on how many of these I take together and encode it, which encoding I am using. There are various encodings, as I said. I told a while back, the public key is actually not in UTF-8 or ASCII. This public key is actually in, some different base 58 encoding. So what are these encodings? Let's go over some of them one by one. ASCII is the most simplest one we understand, which is every byte corresponds to a single text. If these are my 2 bytes, the first one, if you convert this into decimal, it's 89. What is 89? It is Y in ASCII. If I go to this ASCII table over here, I can see 89 is indeed Y, 88 is X. So the same thing, we can see over here. Okay, these bytes can be converted to YX. These bytes, when converted to ASCII, represent YX. But here is another encoding. The bytes are the same, but when you convert them to hex, they get converted. 5958. What is hex? Hex stands for hexadecimal, and it takes 4 bits at a time. Here, first 4 I'm going to represent as the first character. Next 4 I'm going to represent as the next character. Next 4 as the next character. Next 4 as the next character. Hexadecimal takes 4 bits at a time and spits out the final thing. Just like I showed you over here, I said there might be one encoding that takes 2 bytes at a time, one encoding that only takes 4 bits at a time. Hexadecimal only takes 4 bits at a time. And how does it convert from, let's say this to why does 5 come over here? Why does 9 come over here? The answer is, how hexadecimal, the algorithm works. The algorithm works like this. Okay, if you have 0, then it will be converted to 0. If you have 1, then it will be converted to 1. 2 will be converted to 2. So on and so forth. This is the hexadecimal algorithm. It says, if your 4 characters are 0, 0, 0, 0, right? Then this represents 0 in the final character, in the final output. If your 4 characters are 0, 0, 0, 1, what is this converted to binary? It is 1. For 1, you will see 1 over here. What is 0, 0, 1, 0 converted to binary? It is 2. And that is how it will appear in hexadecimal until you reach something like, 2, 4, 8, 1, 1, 0, 0. 1, 1, 0, 0 when converted to decimal is 10. And this represents A in hexadecimal. 1, 1, 0, 1 is B, 11, which represents B. 1, 1, 1, 0 is 12, which represents C. 1, 1, 1, 1, 8, 9, 12, 13, 14, 15. This is 15, which represents F. And this is 14, which represents E. And this is 8, 9, 10, 11, 12, 13, which represents D. And this is 8, 9, 10, 11, 12. This represents C. And 1, 0, 1, 0 is 8 plus 2, that is 10, which represents A. And then this is 11, 1, 0, 1, 1, B. So this is how the hexadecimal algorithm works. Here I will take 4 bits. If they're all 0, then the final output would be 0. If they're all, first 3 are 0, next one is 1, then it will be 1. If they lie in this territory, if they lie after 10, 4 bits can go from 0 to 15, right? You cannot go above it. If I take 4 bits, 0, 0, 0, 0, that gets converted to 0. 0, 0, 0, 1 gets converted to 1. 0, 0, 1, 0 gets converted to 2. The biggest number that can be is 15. 15 se upar ja hi nahi sakta. And all 15 of these, the hexadecimal representation encoding already says that this is how you can convert these 15 types into the final output. This is the final output for hexadecimal. As you can see, it doesn't have every character. It doesn't have ASCII characters. It doesn't have GHI. These are not part of the output only. If you are converting your string to hex, you will see, only these characters. That includes characters from 0, 1, 2, 3 to 9 and A, B, C, D, E, F. Let's Google a hex encoder online. Let's Google a hex encoder. Let's type Harkirat Singh. This will get converted. This is ASCII. You convert it into bytes. You convert those bytes into hex. They look like this. As you can see, the character length doubled because this takes 1 byte, which in hexadecimal is 2 bytes over here. Sorry, 2 characters over here. This takes 1 byte, which in hexadecimal is 2 characters over here. Notice the output characters only have B, they have E, but they don't have, I, J, K, L, M, N, O, P, because the final outputs can only be these right here. That is why base 16 encoding, finally you will have a much smaller set of characters. You will only have 16 characters, but the length will be much longer because every single ASCII character, every 8-bit character gets converted to 2 characters over here. That is how you base 64 encode, which is different from ASCII encoding. This took all 8 bits. This takes just 4 bits. All right, let's look at some code next to understand how can you convert a byte array, something like this, over to hex, and how can you convert hex back to a byte array. Let's look at the code that we've written over here. By the end of it, this code should be able to give us something very similar to what this website does. On this website, if I encode hello to base 64, it looks like this. This gets converted into a bunch of bytes, more specifically 5 bytes. And 5 bytes represent 10 characters in hex encoding, which is why you see 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 characters over here. Let's see if that indeed does happen though. Let me copy this code, open Replit, or you can run it locally. Either is fine. Select Node.js, click on Create REPL. If you look at the code, it defines a function called array to hex, which takes a byte array as an input, returns the hex string. We will get later into how it does that. Let's take this as a black box. What have we done here? We have defined a variable called byte array, which is a new uint8 array with 72, 101, 108, 108, 111. These are the 5 bytes in there. And then we call array to hex, which should hopefully convert this into a hex string. Let's try to run it and see if it does do it. It converts it to 4, 8, 6, 5, 6C, 6C, 6F. And what did this specific website convert it to? It converted it to something else. Can you tell the difference? Can you tell me, or can you guess, why does hello over here get converted to 6, 8, 6, 5, 6C, 6C, 6F? And why does hello over here? Because this also represents hello. Why does this represent hello? Because I can do something like this. S string equal to hello. Const byte array 1 equal to new text encoder dot encode str. This byte array 1 and byte array should be the same, or are they? The second byte array is not for hello with a small h, it is for hello with a capital H. That is why the result that we see over here and the result that we see over here are different. If I make this capital H, then indeed I see 4865 something here, which is what I see over here. So the problem was the byte array that I chose had H as capital. If I now do this, let's say, take the string hello, convert it into a byte array, and then pass this byte array 1 to the function and log the final string. Now I see 6865, this string right here, which was the same thing that hello gets base 64 encoded to. So this code does work as expected. Let's see how does it work. What does the array to hex function exactly do that converts this byte array over to a hex string? First, it defines an empty hex string, a variable called hex string, which is an empty string. Then it iterates over all the array. I repeat, it iterates over the array. The array will look something like this. It will have 5 elements, some H, E, L, L, O, more specifically their byte representation. And it, in every iteration, in each of these 5 iterations, it does hex string plus equal to byte array of I dot toString 16 dot pad start 2, 0. There are a lot of things happening here on the right. So let's try to understand what is happening. Let me open the console here. Let me show you something. Let x equal to 1, let's say. If I do 1 dot toString, it converts, x dot toString, it converts the number into a string, fairly straightforward. Let me do let y equal to 12. If I do y dot toString, can you guess? It converts this 12 over to a string. But if I do y dot toString 16, it converts 12 over to C. Why is that? Can you guess? Can you guess why when I do y dot toString 16 is hexadecimal, it gets converted to a C? Because if you remember, what does 12 get converted to in hexadecimal? It gets converted to C. So what does that tell you? Okay, when you call a number dot toString with hexadecimal representation, or a byte which can go from 0 to 255 dot toString 16, it converts it to its hexadecimal representation. If I write let z equal to, let's say, 214 and do z dot toString 16, it gets converted to D6, because 214 when converted to a binary has 8 characters. I repeat, number 2 bits. 214 when converted to binary has these 8 characters. The first 4 characters get converted to D. The next 4 characters get converted to 6. So that is what the toString 16 function does. But the problem is, as you saw over here, y dot toString gave you C. But y, what was the y variable? 12. When you convert 12 over to binary, it gets converted to 1100, which is actually 00001100. This is its byte representation. So when we convert it to hexadecimal, we want to see 0, and what is the number? 12. What is 12? C. What we want to see is 0C. I repeat, if you convert the string C or the number 12 over to hexadecimal, I don't want to see just this right side. I want to see the first 4 characters converted to a 0 and the next 4 bits converted to a C, which is why we add dot pad start 2, 0. It says here each one of these bytes needs to be converted into at least 2 characters. If the thing on the left, if the byte on the, we have a new uint 8 array. We have a new uint 8 array, which has, let's say, the byte representation of H and then E and then E and then L and then O. H, E, L, L, O. We say, this H will get converted into bytes, a single byte or 8 bits. Let's say, 00001011. Let's say H gets converted to this. It won't, but let's say H ki binary representation is this. Then we don't want this to get converted to a single character. We want here, even though the first 4 characters are 0, first we put 0 over here, and then we put whatever the next 4 bits over here are. We want to pad it with 0 if there is, a single character in the end. If there is a single character for this specific byte, we want to pad it with 0 such that the total length becomes 2. The total length becomes 2. That is what dot pad start 2, 0 does. It says, pad the starting with 0 if the character length is not 2. Let's try that out. Let's do 1 dot pad start 2, 0. It puts a 0 in the front. If I do a 5, 0, it will put 4 zeros in the front so that the net length becomes 5. So that is what this dot pad start does. What does dot toString 16 does? Converts this ith byte over to hexadecimal. Then we pad it with 0. We keep adding it to the hex string and finally return the hex string over here. So this is how you convert a string over to its hexadecimal representation. Do you need to know this? Not really. Eventually, when we'll be using crypto libraries, you can simply do a 2 hex. You'll get a function like this that will simply convert your, let's say, string over to hex or byte array over to hex. So you don't need to learn this. I have added all the codes everywhere to convert, let's say, byte to ASCII, ASCII to bytes, uint8 array to ASCII, ASCII to uint8 array. But you don't need to know this. Even I Googled this, understood and copied over the code here because you never use these functions. Whenever you do have to use these functions, you Google them and, use the algorithm that someone else has written rather than writing it yourself from scratch. Can you write it yourself? Yes, but you need to know. Cool. So that's hexadecimal representation. Similarly, there is base 64 representation and base 58 representation. Base 58 is the one that you want to eventually reach because that is what Solana uses over here. If you look at a public key in Solana, it's actually base 58 encoded. But before that, let's understand base 64 encoding. One character equal to 6 bits. It's as simple as that. Just how we took 4 characters and converted it into a character over here, 4 bits and converted it into a character over here. I would have taken the 6 bits and converted it into a character over here, that would have been base 64 encoding. Base 64 encoding uses 64 characters, that is 26 characters from capital A to capital Z, 26 characters from small a to small z, 10 characters over here, plus and slash. If you add these up, you will get 64 different characters, which means each character can represent one of 64 possible values. Let's look at a base 64 encoder. This though we have commonly used, well, not in this cohort, but in the last cohort when we were doing Kubernetes to encode secrets, if you remember. If I type, let's say HEL over here, firstly tell me, what is HEL converted to bytes? Can you guess? What is HEL when you convert it to bytes? How many bytes will it be? It will be 1 byte for H, 1 byte for E, 1 byte for L. What is 1 byte? It is 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. This is 1 byte right here. HEL would be 3 bytes, 1 byte for each character. What did hexadecimal encoding say? It said, I am going to take 6 at a time. So it will take 1, 2, 3, 4, 5, 6. 6 of these and create the very first character. Let's say the character is A. Then it will take the next 6, 1, 2, 3, 4, 5, 6 and create the next character. Let's say the character is B. Then it will take the next 6, 1, 2, 3, 4, 5, 6 and create the third character. Let's say it's C. And then it will take the last 6 and convert it into a fourth character. Let's say it's D. So just how in hex, what happens, we take 4 at a time and convert it into a character. Now we take 6 at a time and convert it into a character. So if I convert hell over to base 64, how many characters should it be? It should be 4 characters, hopefully. 6, 6, 6, and 6. Let's see. If I encode this, it gives me back AGVS, which is indeed 4 characters as the final output. If I run the code for the same thing, let me quickly do that. There is some code that we have written here that again converts the string hello over to base 64. If I run this, it will be, 1, 2, 3, 4, 5, 6. It's actually just 7 characters. Whenever you see an equal to, it means, it did not have enough characters to make it a multiple of 4. I repeat, whenever you have base 64 encoding, it makes sure there are either 4 characters or 8 characters or 12 characters. So if there is something left at the end, if there were only 7 characters that you could make, it adds a question mark in the end. If you look at this, this is 1, 2, 3, 4, 5. That is 5 bytes. 5 bytes is how many bits? It is 40 bits. In 40 bits, how many 6, lettered elements can you create? How many elements can you create who have 6 bits at a time? It is 40 divided by 6 ka ceiling. The ceiling of 40 divided by 6. How much is that? 6 5s are 30, 6 6 are 36, 7 are 40. It's 7. So ideally, you were only able to create 7 characters, but base 64 always ensures that you have a multiple of 4 characters, which is why it added a equal to in the end. Let's take a different example. Let's take HELL. That will be 8 4s are 32 characters. How much is that? 6 5s are 30. That is 5 characters. But as I said, when you convert a number to hex, if it only has 5 characters in the output, then you need to pad it with 3 equal to's. If I run this with only 4 characters, you will see there are 2 equal to's at the end, because 32 divided by 6 ka ceiling is actually 6. So the first 6 characters you were able to get from the bytes. 72 gets converted into, let's say 10 10 10 10 101, let's say get converted into 11 0100. 108, let's say gets converted to something like this. The first 6 of these you take. And convert it to S. Then you take the next 6, 2 from here, and 4 from here, and you convert it to G, which is the second character over here. Then you take 4 from here, and 1 2 3 2 from here, and that converts to V. Then you take these 6 and these convert to S. Then you take these 6 and these convert to B. And then you take the last 2 and pad it with a bunch of zeros, and that gets converted to A. This should have been your final representation, but since you need it to be a multiple of 4, you pad it with 2 equal to's at the end. Whenever you see equal to's at the end of a base 64 string, it means these are just extra characters they had to put, because the final character length wasn't a multiple of 4. Cool. That is how you do base 64 encoding. And base 58 encoding is very similar, only it excludes a bunch of characters. Specifically, from A to Z does not include I and capital O. In lowercase characters, it does not include L, because L and I look very similar. It tries to get rid of characters that can get that can cause confusion. From 1 to 9, it does not include 0 because it looks similar to O, and it does not include a plus and a slash. So it's all the characters in base 64 minus 1, 2, 3, 4, 5, 6 characters. That's 58 characters. And this is how Solana represents its final address. If you look at a Solana address and copy it, this, if you look at it, does not have O, does not have plus, does not have slashes, because this is the base 58 representation of the underlying bytes. Again, there is code over here that will show how you can encode and decode a string or a bunch of bytes, something like this, over to base 58. Here we are just using this base 58 library that does it for us. And as I said throughout, we'll be using these crypto libraries that will just give us a function that looks like this: base 58.8.encode the uint8 array, and base 58.decode the string back to an array. So you can write the code for them yourself. That's actually a decent assignment to do. Given a string, write a base 64 encoder, or you can use functions like .toString. It's a different one. Hex I wanted to show. .toString 16, that will convert it over to hex. .toString base 64, that will convert it over to base 64, or base 58.encode, which comes from an external library over here to just offload the task of this algorithm over to this external library. These are in what are the encodings we have learned about? We learned about ASCII, we learned about hex, we learned about base 64 and base 58. It is good to know how to write this code that converts from string to its hex representation, or hex representation back to an ASCII string. But usually you will see throughout the slides, that we'll be, reusing a bunch of functions like this. For example, for base 58, there is this bs58 library that just does the encoding and decoding for you. With that, let's move on to the next section, asymmetric encryption, and how can you use it to create your own public and private keys. All right, let's understand encryption and hashing before we reach asymmetric encryption. Hashing is the process of converting data like a file or a message into a fixed size string of characters, which typically appears very random. We discussed this in week 1 as well. It looks something like this. You have a normal looking string like hello. When you pass it through a hashing algorithm, it spits out a fixed length string, and you can't go from here to here. There is no way to convert this random looking string back to hello. The hashing algorithm that we looked at last week was SHA-256. If I search for SHA-256 converter and I type, let's say hello there over here, as you can see, the output is fixed length. And if I change just one character, the output changes by a lot. That is the one of many properties of hashing. If you remember from week 1, it is pre-image resistant, which means given this, you cannot find its pre-image, you cannot find its original string. And even if you change the character a little bit, the output becomes extremely, new and very random. That is what hashing is, something we discussed last week. Encryption is slightly different. As the name suggests, it is you encrypting, which in the name itself, means you can decrypt it as well. You can encrypt the string. You can also decrypt the string. Encryption is the process of converting plain text data into unreadable format called the ciphertext. Using a specific algorithm and key, the data can be decrypted back into its original form only with the appropriate key. So if this is the data, you encrypted it using a certain key, you can also decrypt it using the same key. Here is an example of a symmetric encryption algorithm. What is symmetric? What is asymmetric? We will get to. But for this first example, can you see, given a string and a key, I can convert it over to something very random looking. And look, given that random looking thing and the key, I can decrypt it back to a hello. If I go over here and let's say the string that I want to encrypt is hello, the algorithm, the secret that I have, the key that I have over here is, let's say, this random string. If I click on encrypt, it gives me an encrypted string. If I take that encrypted string and have the same secret over here, I can decrypt it back to hello. So symmetric encryption, specifically in this case, we're using the AES algorithm, lets you convert from a string to something encrypted, but it also lets you decrypt it as long as you have the same key. If I change this key over to something else, then I won't be able to decrypt it. But if I have the same decryption key over here, then yes, I'll be able to get the original string. Why are we learning about encryption? Because eventually you will see, in cryptography, the way to let the blockchain know, you want to send someone funds. I repeat, if I want to send someone funds, the way I prove to a miner, I have approved this message, is by somehow what's called signing or encrypting this message. I will encrypt a message that says, I want to send $100 or $1 to someone else. That is why we have to learn about encryption. But blockchains don't use symmetric encryption. They actually use asymmetric encryption. What is asymmetric encryption? Basically means when you sign it using a different type of key called the private key. Some random looking text comes out. This gets encrypted over to a string. And when you decrypt it using a corresponding public key. This introduces the concept of a key pair. I repeat, when I started the class, I told you, this wallet has a public key and it also has a private key. If I go to this account, click on show private key, put my password here, it will show me a plain text private key. That private key is the corresponding, private key of this public key. This public key right here, key corresponding private key, I can fetch. And given these two strings, I can, encrypt a message and also decrypt a message. Why are we doing this? Because if I ever send a message on the blockchain, I will encrypt it using my private key. That way, a miner can be sure कि यार ये message तो हरकीरत से ही आया था. This message came from हरकीरत, because the miner will decrypt it using my public key, and the miner will be like, I was able to decrypt the message The message says Harkirat wants to transfer $100, and hence the miner can prove that Harkirat has indeed signed a message. The Harkirat has indeed encrypted a message that says he wants to transfer $100. So how do transactions happen on the blockchain? If I have my wallet, which has a private key and a public key, I create a, let's say, plain text message, something like send $100 to Harkirat, and I sign this message. What does signing this message mean? It means I encrypt it using my private key. I encrypt it using my private key. Some random gibberish comes out. I send this over to a miner on the blockchain, a blockchain miner, someone, who's running a miner on, let's say, the Ethereum blockchain, the Solana blockchain, the Bitcoin blockchain, wherever I want to transact. And then this miner will take my public key. I will also send my public key. I will send the message. I will also send my public key. The miner will take the message, which is, this random looking message, and decrypt it using my public key. And this will get converted again back to this message right here. Okay, send $100 to Harkirat. That way, a miner can be sure that ye message jo tha na, the message that I have just received indeed came from Harkirat, because the signing was done by the same private key corresponding to this public key over here. That is why you want to use symmetric encryption, asymmetric encryption in case of blockchains. So what is asymmetric encryption? Asymmetric encryption, also known as public key cryptography, is a type of encryption that uses a pair of keys, a public key and a private key. As I showed you a while back, I have a public key, I have a corresponding private key. The keys are mathematically related, but it is computationally infeasible to derive the private key from the public key. They are related. If you sign something from the private key, public key can decode it, but given the public key, you can't find the private key. If I share my public key with you, send me some Solana, you can't find my private key from it unless you hack my computer and reach this section and are able to find my private key from here. You can't derive it just from my public key. Public key is something you can share with the world. I have shared my public key with you. Send me some Solana. This is my public key. And private key is something you don't want to share with anyone ever. If you share it with someone, they can basically access all of your funds, because now they can, sign a transaction given they have your private key. So this is the usual flow of a transaction before you submit it on the blockchain. And these are some commonly available asymmetric encryption algorithms. You might have asymmetric encryption algorithms. You might have heard of RSA. You might have done it in a cryptography, class in CS as well. It uses prime numbers a little bit. If you've, done this, let me give a quick refresher. It depends on the idea. If you multiply two very big prime numbers, I repeat, if you multiply two very big prime numbers, it gives a very long number. It's very hard to find these two very big prime numbers from, the final string. If you understand this, it's fine. If not, that is fine as well. But P1 is a prime number, P2 is a prime number. If you can find two such prime numbers and, multiply them, the final string that you give out to the world, it's very hard to find P1 and P2 without actually brute forcing for P1 and P2, which is computationally infeasible / extremely hard. So that is the algorithm that it depends on. RSA is not used by all the blockchains that we're going to worry about in this cohort. They actually use something else. They use elliptic curve cryptography. Specifically, there are two algorithms. One that Ethereum and Bitcoin uses called IXDSA. It stands for elliptic curve cryptography. And EDDSA. This is ECDSA. This is EDDSA. This one's slightly more modern and more optimized. But ETH and Bitcoin use this. Solana uses this. This one's called Edwards curve digital signature algorithm. High level, these algorithms depend on something called elliptic curves. As you can see, both of them have elliptic curves in their names. This is what an elliptic curve is. It's a very nice video by Numberphile, if you know those guys. that explains what elliptic curves are. More specifically, how can you use them to, do symmetric encryption and decryption. Feel free to go through it. Not necessary. I did not know this, if I'm being honest, for the longest time. I just kept on hearing elliptic curves back in office. I never knew, okay, these are this is how an elliptic curve works under the hood. So RSA uses prime numbers. These two algorithms use elliptic curves. What do they use elliptic curves for? For asymmetric encryption. And there are many commonly available elliptic curves. One might, look like this. One might, be a little wider. These are the two commonly available ones. The first one, this has a full form which I'm forgetting now. This is used by Bitcoin and Ethereum. The second one, ED25519, you'll hear this term very commonly. This is what Solana uses. ED25519 is an elliptic curve that looks something like this, that Solana uses for doing asymmetric encryption. More specifically, that Solana uses to generate this public key and the corresponding private key. Cool. What do we learn from this slide? We learned that there are various algorithms for asymmetric encryption, just like there are various algorithms for hashing, SHA-256 being one of them. There are various algorithms for asymmetric encryption. Let me actually, write this down so it's a little easy to digest. What I'm saying is, for hashing, there are two algorithms that we heard of used. There was SHA-256 and there was MD5. For symmetric encryption, I repeat, for symmetric encryption, we learned about one algorithm. What was that algorithm called? AES. We just tried it out in a browser. And for asymmetric encryption, I repeat, for asymmetric encryption, we heard about three algorithms: RSA, EDDSA, and ECDSA. This one's used in BTC and ETH. This one's used in Solana. What is it used for? It's used for generating public and private keys that follow these formats, that follow these conditions right here. Okay. But it is computationally infeasible to derive the private key from the public key. In the next slide, we will understand how can you create these public and these algorithms. How can you create an Ethereum and Bitcoin public and private key? How can you create a Solana public and private key using if you've ever deployed a certificate, an SSL certificate, this also has a public and a private key. Certificate, you just run a few commands to generate the public and private key. You don't write the algorithm from scratch, even though you can. You use a publicly available library that will generate a public and private key for you. Cool. With that, let's understand how can you generate a public and ECDSA and EDDSA. Again, this uses this elliptic curve, and EDDSA uses ED25519, this elliptic curve. What are elliptic curves, Harkirat? They're basically a curve on the graph that looks something like this. This has an algorithm x square equal to y cube plus some x, something like that. If you look at it, this is just, an x and a y axis. And, this is charted out as a curve over here. The curve follows a certain algorithm that looks, one of these two, x square equal to y cube plus 2x, or I think y square equal to x cube plus, some constant into x. I think it is this. I could be wrong, just Google it. And if you plot this out on a graph, it looks something like this. If you don't understand this, it is fine. The thing to know is, we use elliptic curve cryptography to generate public and private keys in blockchain. We use RSA to do, other things which are not blockchain related. Cryptography can be used for various use cases. For example, if you've ever generated SSH keys, and if you haven't, you should by now, because we'll be needing it very soon. But they look something like this. If you've ever run the command SSH- keygen to generate an SSH key, when you generate it, you give it the algorithm to use. In this case, I'm telling it to, use the ED25519 elliptic curve. And you do this eventually when we reach the Git class in the web development cohort. We will learn this. You do this so that you can prove to GitHub that this is Harkirat, and you can push to GitHub repositories. If you've ever gone to any GitHub repository, for example, let me go to github.com/code100x/ or 100x devs code 3 assignments, you will see it gives you a secure shell option over here, or SSH option over here. When we use this in the Git class, we will understand, how SSH keys are created and how they are also public private key pairs, very similar to the ones used on the blockchain. And the third use case of public key cryptography is blockchains. To recap, what have we learned? We've learned about asymmetric encryption. We've learned about various algorithms to generate the private and the public key for the asymmetric encryption. We've learned about elliptic curves and how they are used in some of these algorithms. And lastly, some commonly available use cases of public private key pairs. The one that we'll be focusing on is this one right here. Let's get into the next slide and understand how can you create a public and a private key pair for a given algorithm. Right. Can you create a public private key pair from some of these algorithms? What is our goal in the end? Okay, we are able to generate a public private key. We're able to sign a message using the private key and then ensure that the public key can actually verify the message. That is our goal, right? We want to create something like this. To create a wallet, number one, you need to be able to generate public and private keys, this red thing right here and this red thing right here. Number two, you should be able to sign a message using your private key. And just so that we are able to understand how things work, we will also decrypt the message using our public key. That is the code that we'll be writing in this specific section. Specifically, we'll do 5 things. First, generate a random public private key pair. Then define a message to sign. This could be hello, hi there, whatever message you want. Convert the message into a uint8 array. Sometimes we will do that. Sometimes we will convert it into hex. Whatever the library expects from us. Given this message, we will convert it into a format, encode it into a format. Then we will sign the message using the private key. We will verify the message using the public key. These are the 5 set of steps we are going to follow for both the curves that we discussed. We discussed EDDSA algorithm that uses ED25519. We discussed ECDSA that uses SEC256K1. We'll understand how you can write the code to do all these 5 steps from top to bottom. Now there are 2 sets of libraries I'm using. One that, exists without blockchains, by which I mean, this is a library that you can use to generate public private key pairs using the ED25519 algorithm. Before Solana was a thing, Solana and Ethereum thankfully introduced some libraries that you can use that make your life slightly easier. But let's say Solana did not exist, Ethereum did not exist. Then also this is a commonly used algorithm for other things. So now that Solana exists and Ethereum exists, the engineers at Solana have written a library called @solana/web3.js. The engineers at Ethereum have written a ethers library. So you can just use this. This gives you very nice high level functions. For example, a function like keypair.generate that will generate the public and the private key for you. Or you can use, libraries like @noble/ed25519, which if you look at this, library, let's Google what this library does. If you open the npm page of this library, it says this is the fastest JavaScript implementation of ED25519. So this is one library that irrespective of blockchains can generate public private keys for you. You can use it for signing for various algorithms. And @solana/web3.js is, a library that the Solana engineers have created to make your life a little easier if you are building blockchain specific use cases. If you are building a wallet only on Solana, then just use this library. If you are building something else, then you can use @noble/ed25519. This under the hood uses this only. @solana/web3.js just creates some top level functions that generate the public and the private key. But under the hood, this also uses @noble/25519. And then similarly, these are the libraries for generating Ethereum or Bitcoin public and private keys. Let's kick things off with the first one, which is generating a Solana public private key that uses EDDSA algorithm. I've written some code over here, and now this is TypeScript code. So the only thing you will have to keep in mind is when you go to Replit to test this out and run this, click on create REPL and select TypeScript as the environment over here. Don't select JavaScript. That's the only thing you have to keep in mind. We aren't using very strict TypeScript here, so it should be easy for you to understand. Let me paste this code over here. And let's look at this code. What does it say from the top? First, it imports star as ed from @noble/25519. Very similar to what's happening over here. The first line of code here, what does it say? It imports this library in a variable called ed. Now this is slightly different from, const ed equal to require @noble/ed25519, just like we've been doing until this point. But hopefully you understand, this and this are doing the same thing, only this is a slightly more modern syntax to do it. Then we define a function called main, which is an async function. Now, if you don't know async await in JavaScript, then, this will be slightly hard to digest. We have covered this in the web dev cohort in a video. So I would urge you to go there to understand what an async function is. How is it different from a normal function like this? We define an async function called main. We call it over here. What is this main function doing? It is first generating a random private key. ed.utils.random private key is a function. When you call this function, it will return, as the name suggests, a random private key to you, something that looks like this. Then we define a message called hello world. We convert it into a uint8 array. If you remember, new text encoder.encode hello world would convert hello world into a uint8 array. And that is what, we've done in this line of code. Then we get the public key from this key pair. This is the private key. From this private key, we get the public key. From the private key of a wallet, you can derive the public key. From a public key, you cannot derive the private key. I repeat, from a private key, you can always derive the public key. If you have someone's private key, then you can get the public key. From the public key, you cannot derive the private key. So we get the public key from here. We actually sign the message. How do we sign the message? ed.signAsync. Notice it is an async function. In the name itself, it has ed.signAsync, which is why we have to put an await in front of it. Similarly, get public key is also an async function, which is why we have to put an await in front of it. This will give us the public key. This will sign the message and give us a signature. It will basically give us, sorry about that, this thing right here. We are generating the public private key. We are signing a message called hello world and converting it into a signature in this line of code. And then in the next line of code, we are checking, is this signature valid for this message and this public key? Is this signature valid for this public key and this message? That is what this line of code does. What is it doing? It is verifying, is this signature valid on this message and this public key? What did asymmetric encryption say? Given the signature, given the encrypted string, you can decrypt it using the public key, or the other thing that you can do is, or what this is called is signing the message. What we have done here is generated a signature. And what is this second step called? It's called verifying. It is called ensuring this specific signature is indeed for this message and checking it using this public key. Finally, we log is valid on the screen. Let's try to run it and see what comes. It prints true on the screen, which means control reached here. Main was called, a private key was generated. Let's log the private key. Then the public key was generated. Let's log the public key as well. Then we generated a signature. We signed using the private key. This line of code does what? It does this part right here. And then we verified using the public key of the user, which is this part right here. Then we log is valid. If I run this now, you will see a private key and a public key gets printed. Again, they appear as byte arrays, but you can always convert them to base 64, base 58, hex, whatever you want to convert it to. But by default, they are byte arrays of 32 bytes. So 32 byte array for the private key, 32 byte array for the public key. What have we done in this specific, code over here? To recap, we've called a main function which generates a private key, generates a public key, signs a message, verifies the message, and logs whether or not the verification succeeded. Can you guess what happens in the real world? When I go over here, number one, a public and a private key was generated for me. When I try to send a message, let's say I want to send Solana to some random address, and the amount that I want to send is 0.01. If this was a valid address and if this is a valid amount, if I click on next and send, what do? I sign a message. I sign saying I want to send 0.01 Sol to this address. And then where does this verification happen? This happens on the miner. The miner actually verifies, is this signature actually done by Harkirat? And if it is, then the miner can introduce this in the block. That is what happens on a blockchain. This is everything happening on one single machine over here. But on the blockchain, again, what happens? Let me show you this on the iPad. And we'll see this very soon in the slides as well. Okay, on the blockchain, this is my computer. And this is a miner, let's say. What happens is if I ever want to send someone money, I first create a message like this. Send $10 to this other random address. I sign it using my private key. I already have a private key and a public key. You just saw this in my Phantom wallet. I sign this message, convert this into some random gibberish. I send this random gibberish over to the miner along with my public key. This is my private key. This is my public key. I also send my public key to the miner. The miner verifies, is this true? Is the person actually trying to send $10? Is this a valid signature? And if it is, then the miner will include this in the next block. That way, you can be sure if the money is ever spent, if money ever leaves my wallet, I repeat, if the money ever leaves my wallet, if there is ever a transaction on the blockchain happening for this wallet, then I signed it. So, either my private key is leaked or I am the one who actually sent the message. If I leak my private key, then of course other people will pull out my money. And if not, then I was indeed the person who sent the message. This can be verified by every miner because every miner has my signature and my public key. They will be like, this message was signed using this public key, and hence we know Harkirat approved this transaction. That is the significance of asymmetric encryption here. Okay. The message body usually looks something different. The message body looks like I want to send $2 to Harkirat. You encrypt it using your private key. The miners verify it using your public key, and you go from there. This is exactly what we have covered in the slide number 8. If you open slide number 8, at the top, you'll find this link to blockchain that we discovered last week as well. Click on public private key pairs and signing, and you will see this whole, architecture slightly more visually. You generate a public and a private key. You can randomly generate it locally. You generate this locally. You never have to ask the blockchain, give me a new public private key pair. No, you generate a random public private key pair. Given this private and this public key, you can create signatures. You can sign a message that looks like this. Send $10 to Raman, or some other public key that looks like this. If I sign the message, I get a message signature. That is exactly what was happening here. I was generating a private key, generating a public key, and I was generating a signature, signing this message. Now this message can also be, I want to send $10 to Raman, or more specifically, 0.1 Sol to Raman. I sign the message and generate the signature. Signature looks something like this. And on the blockchain, the miners can verify, given this signature and this public key, was this message created using it? Since this is green, it means yes. If the signature is incorrect and I verify, the miner will reject it. The miner will be like, Harkirat has not approved this message. This signature is incorrect. So I need to make sure the signature that I'm sending to the blockchain is a valid signature. It indeed signs this specific message. If you look at the transaction, this is a slightly more cleaner way to look at it. Okay, the message that you sign is, I want to send $20 from my public address to this other public address. The same thing that I wrote in the last slide, right? Here I wrote it textually something like this. This is just more, in 3 separate blocks, still the same thing. Okay, I want to send $20 from here to here. If you sign this using your private key, this is the signature that comes, and you submit it on the blockchain. What is the blockchain in the end? It is just a bunch of blocks like these, a bunch of transactions like these. For example, this is the very first Genesis block. Genesis block means कि यहाँ पे तो कोई transaction हुई नहीं. No transaction happened here. Just $100 was sent to the miner. The Coinbase means, whatever is printing the coins. 100 transactions were sent to the miner over here. Then the second block onwards, transactions have been included in the block. $10 need to be sent from here to here. $20 need to be sent from here to here, $15 need to be sent from here to here, and a fourth transaction. And all of these have been signed by whoever is transferring the money. In this case, only one person has the money. In the first block, only one person got money. So in the second block, of course, only that person can spend that money, which is why, this, and this are all the same person. That would have happened in Bitcoin as well, right? The initial block, the Genesis block, gave all the Bitcoin to, let's say, a person X. In the second block, only the second person can send money. No one else has Bitcoin. Then in the third block, more people can send money, so on and so forth. So a single block has multiple transactions. This specific person will take all of these transactions and mine. If you remember, they will find a nonce, which, when this combined with that nonce hashes to something that starts with a certain number of zeros. Okay, confused? Let me recap. Now we are using both encryption as well as hashing together. What did we learn in the first week? Okay, if this is the Bitcoin blockchain, what does each miner do? First, it accepts a bunch of transactions from a user's. Transaction 1, transaction 2, transaction 3. It creates a block from it. A block basically means, a bunch of transactions one after the other. Then it finds the nonce. It finds a number. It does mining to find a number such that when you put that number in front of it, let's say that number is 25561. When you hash all of this together, you get 0000x, something like that. You hash. The miner is hashing. The person who's submitting the transaction is encrypting. I repeat, or more specifically, signing. You as the person, as a user of the blockchain, sign a message, you submit it on the blockchain. The miner verifies the message and then hashes the block into, something that starts with a certain number of zeros. That is how proof of work works. That is how this blockchain works. If you look at all the steps, user first creates a public private key pair. I created my own public private key pair over here. They create a transaction that they want to send, let's say 50 rupees on the blockchain. They hash the transaction, or they encrypt the transaction. Well, they hash the transaction and then encrypt it. Feel free to ignore this step as well. It basically means, whatever step you have taken over here, whenever you send someone this message, you're not signing. You are not signing, I sent $10 to this. You actually first hash it to, convert it into a simple fixed length string. And that hash is what you submit on the blockchain. They sign the transaction using their private key, and then they send the raw transaction, the signature and their public key to a node on the blockchain. What do they send to a node after they've done all of this? They send to the blockchain, कि यार ये रही मेरी transaction. This is my transaction. This is the raw transaction. This is the signature for that transaction. This thing right here. And this is my public key. You can check कि when you convert this raw transaction into a hash, step 3, you can verify using my public key कि I indeed signed the message. That is what the user does. That is how you transact on the blockchain. To repeat, how do you transact on the blockchain? You have your own machine. On this machine, you have a public key and a private key. We just showed you how can you create a public and a private key. You first write this message down. Okay, I want to send $10 to XYZ. Then you hash this using, let's say, SHA 256. Then you sign this, and this signed message and your public key and the original message is what you submit on the blockchain. Using these three, the miner verifies, was this transaction in? The miner will introduce your transaction on the block and then, start to mine with a bunch of these transactions. Whenever they're able to find the nonce, they will tell everyone else, okay, yaar, I have won this battle. I have been able to mine first. So, the first transaction belongs to me. I get $100 because I'm the miner, and then everyone else has their. These are the transactions I would like to introduce in this block. That is how the blockchain works. What happens on the miner? Hashes the original message to generate the hash, whatever was happening here. Verifies the signature using the user's public key and the hash generated in step 1. The miner validator checks additional aspects of the transaction, such as ensuring the user has sufficient funds. You can send any message. You can send, I want to spend $1 million, but the miner needs to check whether or not you do have $1 million. And if that checks out, they can just add it to the block. And eventually they start mining. After they have sufficient transactions here, they can start mining. Once they're done mining, they will generate the nonce and submit it to all the other nodes on the blockchain. That is how the blockchain works. But what is the step one? User needs to create a public private key pair. How can you do it? You can use the @noble/ed25519 library, or thankfully, every blockchain gives you top level libraries. What do I mean when I say top level libraries? I mean, they just under the hood use this. They give you high level functions that you can call to, generate a key pair, to sign a message, to verify a message. That way, you don't have to worry about low level APIs like these. So let's look at the code for @solana/web3.js, which is, usually what you will use if you ever want to create a public private key pair for Solana. If you ever want to create a public private key pair for Solana, you would use this library rather than, going to the underlying library like this. Let's look at the code. This one's much simpler to look at, right? Const key pair equal to keyPair.generate, where key pair is a class that comes from here. Now you might ask, Harkirat, if key pair is a class, why am I not doing new key pair over here? We to have learned that classes are written like this. How are you calling keyPair.generate? And the answer is this is a static function. We haven't covered static functions, so don't worry about it just yet. But the reason, I was able to call a function on a class, if you hover over it, if I go inside, you will see keyPair is a class. But the reason I was able to call a function on it, because the generate function is actually static. What are static functions? Don't worry about right now. But this function generates a key pair for you, a random key pair. This is how you get the public key. This is how you get the secret of it. You can log the public key. You can log the private key over here. I think you can also do 2 base 58 if you want to see it. The base 58 encoding, which is what I shared. The public key over here is present on. If I run this, let's just look at this and this first. Ignore everything else. Public key is the same as the public key you saw over here. I mean, it's not the same, but we were now able to generate a Solana public key using the @solana/web3.js library, and also generate the corresponding secret, which again, is a 64-bit byte array in this case, because I think the last 32 bytes are just the public key. Let's just log the public key and ensure that is the case. If I run this, can you see the last 32 bits here are actually the public key only? We saw previously, the secret is 32 bytes and the public key is also 32 bytes. Here, the secret is 64 bytes. The reason for that is, the last 32 bytes are nothing but the public key over here. That is why the secret looks so big. In the end, the secret is only this big, and the rest of it is just the public key over here that you can separately log as well. You can log it as bytes. You can log it as a string based on, however you want to encode it. This was the whole point of us learning encoding. Public key are more human readable like this. So, we should probably encode them this way. But can you also send your friend a bunch of bytes? You can send your friends a bunch of bytes. Ye raha mera public key, send me money over there. That is also valid. But of course, this is much more human readable. You might want to send your friend this. For example, I was shooting a video with Samay. He gave me his public address like this. He did not give me a bunch of bytes. Ye lo my public address. This is just more human readable. All right. That's how you log the public key. That's how you log the secret. The last bit is how can you first encode a message into a bunch of bytes. I hope we understand this line of code now. And then sign a message, verify the message. This would usually happen on your local machine. This would happen on a miner. So this is how, you create the same thing we did in the last slide, the same thing we did over here, but using the @solana/web3.js library. And this only gives you, key pair related constructs. So if you want to sign and, verify, maybe there is a function here that lets you sign as well. But usually you use this NaCl library, which is a very famous cryptographic library for signing as well as verifying a message. So what is being done over here? We are converting this message again into a signature. What is being done over here? We are verifying. Was this message and this signature, is this signature valid for this message using the user's public key? What the miner would do on the blockchain. By miner, I mean, MINER. If you run this, it prints true at the end, which pretty much tells you, you were able to verify the signature given this, message as well as this public key. Again, what are we doing here? Creating the public private key pair. Let's just put them on the sides. Let me put this on the right. Let me put this on the left. What were we supposed to do? Generate a public private key pair. That is what I've done here. Define a message to sign. That is what I've done over here. Now, where have I defined the message? This is where I've defined the message. This is where I've, converted the message over to new uint8 array. Then I've signed the message over here. Then I've verified the message over here. These were the 5 steps we were supposed to do for the Solana blockchain. We were able to do it here. We were able to generate the Solana public private key pair, sign a message, verify a message. The same thing we can do for the Ethereum blockchain or Bitcoin by using, this @noble/sec256k1 or using the ethers library, which, as the name suggests, is a library written by the Ethereum folks, which, again, if you look at it, what does it do? It generates a wallet. Solana generated a key pair. They call their, public private key a key pair. These guys call it a wallet. Public key is this, private key is this. This is the message you want to sign. This is how you sign the message and generate the signature. This is how you verify the message and ensure, the recovered address when you're verifying the message is the same as the user's public key. Cool. This is how you do the same thing using ethers. And, if you want, you can look at this @noble/sec256k1 as well. Which one should you use, Harkirat? Depends. If you're creating a wallet, usually I've seen them use lower level libraries like these. But for any other use case, if you're building anything on Solana, you use this. If you're building anything on Ethereum, you can use this. Cool. That is how you create a public private key pair. Next up, we've already gone through this. How do transactions work on the blockchain? Let's understand one shortcoming of public private key pairs and what are again, I'm going to spell this really bad. Hierarchical deterministic wallets. Hierarchical means hierarchy. I hope you understand that. I can pronounce that a little bit better. Deterministic wallets or HD wallets. Actually, what we've learned until now is good enough. But if you want to support multiple wallets, if you want to create something like this, then you need to understand what are HD wallets. Let's understand that next. All right. Let's understand what are HD wallets. Why was this introduced? This wasn't introduced initially. It took some time after, a few iterations of Bitcoin, HD wallets were introduced. Let's understand what they are and what problem they solve. Why most wallets you see over here will under the hood use HD wallets. Hierarchical deterministic wallets are a type of wallet that can generate a tree of key pairs from a single seed. This is pretty much the crux of it. Okay, given a single seed, it can generate a bunch of public private key pairs. This allows for generation of multiple addresses from a single root seed, providing both security and convenience. I don't know about security, but it does provide you convenience. Have any of you seen this video ever? Does this ring a bell? If not, let me show you the original video.
All right, so you bought some crypto.
Oh God, this is like... From here onwards, there's basically police catching a random car on the screen, on the street, and inside they found this.
Body cam footage showcases a suspect's seed phrase after an officer unwraps a folded paper.
Logger. Initial.
This is a crypto phrase.
What did the guy say? The policeman said this is a crypto phrase. So what did we learn from this? Most people, when they have a wallet like this, they actually have a single seed phrase. I repeat, they have a single seed phrase, the same thing the policeman saw right now. And from that single seed phrase, you can create multiple wallets, each wallet having, its own public key and its own private key. So whenever I go to Phantom and click on plus over here, I am just creating a new branch of this tree. I am just creating a new public key and associated private key. Why are we doing all of this, Harkirat? For convenience, right? You have to maintain multiple public private keys if you have multiple wallets. If we don't do this, then, I have to back up all the private keys over here. If I have 6 wallets, I will have to back up their private keys in my locker so that if I ever by mistake my laptop dies, or if I uninstall Phantom, using those private keys, I can, reinstall my wallet over here. I will have to maintain 6 different set of private keys, versus if I'm using HD wallets, then I just have to keep this single seed phrase safe. As long as this is safe, I can generate the original accounts that I had. This is deterministic. Given a single seed phrase, you can generate the same public private key again and again from it, as long as this is safe. All your wallets that you see over here, account 1, account 2, account 3, can be derived from that single seed phrase. The solution was actually introduced in BIP 32. BIP stands for Bitcoin Improvement Proposal. Bitcoin, Ethereum are all, improved over the years. And the way they are improved is people put out proposals. KR, this is the problem and this is how we want to fix the problem. In BIP 32, provided the solution to this problem in 2012, it was proposed by this person who's a Bitcoin core developer to simplify the recovery process of crypto wallets. The reason this is introduced is so it's easy to recover wallets. Most crypto people that you will see always have, this phrase like this somewhere in their locker, somewhere, deep down in some alley. In fact, there is this thing called the crypto steal. I repeat, there is this thing called crypto steal, which, as the name suggests, the mother of all backups. What is it? It pretty much looks something like this. It's, a very big steel thing that you get. And here you can put your seed phrase, first 12 characters, then next word, rather than putting it on a piece of paper like this guy did, because paper is perishable, steel isn't perishable. So, the people have literally built businesses around storing this seed phrase. Why? Because this seed phrase sort of holds all of your wallet. A single seed phrase can be used to generate all of your wallets, which is why, people keep this very safe. You can keep it on a piece of paper or somewhere else. Question is, how does this seed phrase derive various wallets? What exactly happens when I click on the plus button over here and create a new wallet? How can you do the same? A few people already did this assignment last week, but how can you do the same? Have this seed phrase and let the user create multiple wallets from it. Let's understand that in the next slide. How to create a wallet? Let's first go through the onboarding flow for Phantom. I repeat, let's go through the onboarding flow for Phantom. Let me open another browser here, something like Brave. Just give me 1 second. This is my Brave browser. Let's say I'm a very new person to crypto. Then what I would do is I would, number one, create a wallet for me. I would download a wallet. So I went to phantom.app. I clicked on download. I selected Chrome as my browser over here. More specifically, I should have maybe selected Brave, but I think they will both lead to the same place. I already have Phantom. Let me remove. I don't know if I want to remove it actually. Let's see. Let me remove it from Brave so you can follow along and try to do the same thing. Let me add it back to Brave or Chrome or wherever you're adding it. As soon as Phantom is added, you will see it generates this onboarding screen for me. This is again common for all wallets. Whenever you create any wallet, be it Backpack or Phantom, it will first take you through this onboarding flow. And what do you think should happen in this onboarding flow? In this onboarding flow, the user should generate their secret recovery phrase. The user should generate those words. Create new wallet. This is a local password. This has nothing to do with my seed phrase. This is just a local password. For example, if I open Backpack, it asks me for my local password. Similarly, this is just a local password. If I click on continue, it says secret recovery phrase. This phrase is the only way to recover your wallet. Do not share it with anyone. Keep it very, very safe. Can you see there are 12 words over here? Do these 12 words look very similar to what this person had written on the piece of paper? This person had 24 words. You can have a 12 word seed phrase or a 24 word seed phrase. But this hacker or whoever this criminal was, they also, created a wallet like this and, put all of their funds over there. Now you're all done. You have that seed phrase. Hopefully you have kept it safe. If you don't keep it safe, let me take a screenshot of this. If you don't keep it safe, then your money is lost if your laptop ever dies. If your laptop is alive, then it is fine. You have your private key in here. But if your laptop dies, if your laptop crashes, then your seed phrase is gone forever. You will lose all of your crypto. You don't have access to it anymore. Your private keys are derived from this. If you lose this, you lose all of your crypto. You don't lose it, it just stays on the blockchain forever. You can never generate the private key for this public key again. I repeat, if you lose this and your laptop dies, then whatever is the private key for this public key, you cannot create anymore, which is why, you don't lose your funds. They just stay in this address forever until eternity. You cannot recover them. Given this seed phrase, an account 1 was created for me. And now if I click on plus and create a new account, an account 2 gets created for me. Click on plus, create a new account, an account 3 gets created for me, so on and so forth. How am I able to create so many accounts given a single seed phrase? The answer is HD wallets. What was the definition? HD wallets are a type of wallet that can generate a tree of key pairs from a single seed. This single seed say I can generate, key pair number 1. What is the key pair of this? This is the public key, and the private key I can get from settings, account 1, show private key. Oh God, I put the wrong password or what? I forgot my password. I think I put something wrong. The local password that I created was incorrect. But if it was correct, if I remembered it, if I would have clicked on next, I would have seen the private key associated to account 1's public key. And similarly in account 2, I can go to settings. I can go to account 2, show private key. It will show me the private key for account 2. So I was able to generate multiple public key, private key pairs given the single seed phrase. So what is the benefit of HD wallets? Why was this big Bitcoin improvement proposal introduced? It wanted to improve Bitcoin. How did it improve it? By introducing HD wallets. KR, let's provide the user a way to have a single seed from which they can derive multiple public private keys. If their laptop ever crashes, if they ever lose access to their laptop, if their phantom ever dies, if they remove this extension by mistake, as long as they have this seed phrase, they will be able to derive all the wallets. They will be able to get all of their public private key pairs back. That is what an HD wallet does. Now let's understand some terms that you need to know before you can create your own HD wallets. The first one is called mnemonics. A mnemonic phrase is a human readable string of words used to generate a cryptographic seed. There is one thing I did not share with you. This is a seed. This is not these 12 characters. These 12 characters are just easy for me to write on a paper, which is why you use this. This is my mnemonic. From my mnemonic, I generate the seed. From this seed, everything can be, derived. So if you look at the slide, what did it say? It said a mnemonic phrase is a human readable string of words used to generate a cryptographic seed. So from this, a cryptographic seed is generated, a very long string is generated. From that cryptographic seed, you can generate multiple wallets. So mnemonic is a human readable string of words used to generate cryptographic seed. BIP 39, Bitcoin Improvement Proposal 39, defines how a mnemonic phrase can be generated and converted into a seed. So BIP 39 was introduced later. It tells you how can you use this mnemonic, convert it into a seed phrase. Here is some code of how this is done in Backpack. If you look at Backpack, what does it say? Const generate random equal to async function, words equal to generate mnemonic. If you need 12 characters, then 128 bit. If you don't need 12 characters, then 256 bit. Set mnemonic words.split space. So what this is doing is, let's look at the generate mnemonic function. What does the generate mnemonic function do? It comes from this library called BIP 39. Whenever the Bitcoin Improvement Proposal 39 was introduced, a corresponding JavaScript library was created, which has a function called generate mnemonic, which will generate either a 12-word seed for you or a 24-word seed for you based on if you need a 128-bit seed or a 256-bit seed. The inputs that it takes is 128 or 256. If you give it 128, it will return you a 12-word seed. If you give it 256, it will return a 24-word seed. If you want to try it out, let's try it out. Let's copy this line of code. Let's go to Replit. Let's generate mnemonics on our own. Let's select TypeScript over here. Make sure you select TypeScript and not JavaScript. Import generate mnemonic from BIP39, and then let's call generate mnemonic with 128. Const words equal to generate mnemonic console.log words. What gets printed on the screen? 1, 2, 3. Can you see a 12 word phrase was generated? Let me pass in 256 over here. Can you see a 24 word phrase was generated? So BIP39 describes how can you generate a mnemonic more specifically. It gives you these words. BIP39 has this list of English words. Here select any 12 random or 24 random strings from it. That is enough randomization. Every word that you see over here, I repeat, every word that you see here, proof, is part of this list. If you see a word called tornado, it is part of this list. So what is this library doing? Generate mnemonic function. It is picking 12 random characters from it or 24 random characters from it. And in this case, printing them on the screen. In case of a wallet like Phantom, they show it in the UI. So building a company or, app like, now this is locked forever. I don't remember its password. But building a company like Phantom and Backpack isn't too difficult. Building a wallet is actually pretty easy because as you can see, you have to generate a seed phrase. There's a library that does it. There's a generate mnemonic function you call and you just show the user their mnemonic on screen. The user needs to back it up somewhere. That is, as you can see, exactly what happens in Backpack as well. So if you go through the onboarding flow in Backpack, which is another wallet, you will see create new wallet, select Solana, click on next, and it shows you a seed phrase here as well. So it's the same thing irrespective of which wallet you are using. And in case of Backpack, this is the code that actually does it. This Coral XYZ/Backpack has the code of Backpack. This specific, mnemonic input.tsx has the code for React code for this screen. Now, if you don't know React, this will be a little hard to read. But yeah, I hope you understand how, mnemonics are generated by most wallets. Given you have this mnemonic, the next step is you convert it into a seed phrase. I repeat, this diagram that I showed you, the mnemonic is used to generate a seed. From the seed, you can generate multiple public-private key pairs. But the first thing you have to do after you have the mnemonic is generate a seed for it, which again, there is a mnemonic to seed synchronous function that BIP39 itself has that you can use. So what can I add over here? Let's see. Go to Replit. After I've generated the words, after I've generated the mnemonic, I can call the mnemonic to seed sync function, which again comes from BIP39, and generate my seed phrase. My root seed I can create. My root seed. Why do I say root? Because this is the root of the tree. And from this, I can generate multiple public-private key pairs. If you look at the Backpack code again, it has this file called keyring.ts, where every sort of blockchain in Solana, you generate, a Solana HD keyring, which is, a class. If you look at this, it is a class that is defined over here that has all the Solana logic for signing and, verifying. And then similarly, there's an Ethereum keyring. The thing to notice here is this line right here. The seed phrase that is stored in each one of these wallets is, what comes from this mnemonic to seed sync function that comes from BIP39. So anytime you create a wallet on, Backpack, anytime you go over here, you go through the onboarding flow, you select Solana and, you create a Solana wallet. This thing is actually converted into, a seed phrase. Where is it converted? It is converted over here, wherever it was. Let's see. If you don't understand this one, it is fine. This file is actually fairly complicated, this keyring.ts. But if you look at it, where is it present? Source services, Solana virtual machine keyring. And this is how you generate a Solana keyring. Keyring basically means this will generate a bunch of keys in the future. This is the seed for it. We store the mnemonic as well as the seed in this Solana HD keyring class. If you don't understand this, it is fine. It is just generating a Solana hierarchical derivable keyring. That is the name of the class. This is a human written class only. This is written by a developer only basically, which, extends this. Don't worry about what this is, what is implements, what is this thing. I'm happy to dive deep into this code base. But hope you understand this much. Okay, given this mnemonic, I generate a seed. Let's log the seed. Let's see what comes on screen. The seed is again a bunch of bytes. It's not a uint8 array, it's a buffer, pretty much the same thing. It is a bunch of bytes that are stored in this seed. And now from this, you can generate various public private key pairs. The one extra thing I would like to introduce here is something called derivation paths. How, as I said, this needs to be deterministic. Given a seed phrase, the first wallet from it needs to be a certain public private key pair. The second wallet from it needs to be a certain public private key pair, so that even if you ever lose this, agar ye gum gaya, if this crashes, if you had to uninstall this, if I go to manage extensions and uninstall, remove Phantom from here, how will I recover my public private key pairs? I have so many of them. How will I recover them? They need to be deterministic in nature. Kya is single seed phrase se, if you pass it through this derivation path, I repeat, given this seed phrase and this derivation path, the first public private key pair is generated. For example, this public key and private key might be generated from this derivation path. What is a derivation path? Here from the seed phrase, if you go down this path, m/44/60/0, this public key and private key comes. Now, what is this? What is m? What is 44? We will get to. But do we thoda understand that given a seed phrase, given the seed phrase I used to create this, how can I create the first public private key, create the second one? I will just change the last character here to be 1. I want to create the first wallet. I want to create the second wallet. Given a seed phrase, you can generate multiple wallets. That is exactly what a wallet like Phantom does. And derivation paths specify a systematic way to derive various keys from the master seed. What do I have over here? What did I log over here? I logged the master seed, the root seed, the thing that is present over here. And from here, I can generate multiple public private key pairs. They allow the users to recreate the same set of addresses and private keys from the seed across different wallets, ensuring interportability and consistency. I can literally have the same set of wallets open in Phantom as well as Backpack if I use the same seed phrase. They allow users to create the same set of addresses and private keys from the seed across different wallets, be it Phantom, be it Backpack. If I put the same seed phrase there, if I open Backpack and I'll write import wallet and I paste my, phrase over here, then I can have the same set of wallets in Backpack as well as Phantom. It ensures interportability. You can easily move from Backpack to Phantom to a third wallet if you are using a certain, derivation path. That is what derivation paths allow you to do. The derivation path typically expressed in this format. Now, some of these are relevant for us, some of these aren't. You'll look at this very soon in the Backpack code as well. But M refers to the master node or the root of the HD wallet. So you will always see M at the beginning of this. / the first thing over here represents the purpose of this wallet. A constant that defines the purpose. 44 is for BIP44, which is a standard for HD wallets. So there was another Bitcoin improvement proposal called BIP44. Bitcoin Improvement Proposal 44 is a protocol that provides a structured method for creating and organizing keys in a deterministic wallet. So most of the times, whenever you're generating wallet, this will be hard coded to 44 only. You can maybe, use a different type of proposal or a different type of algorithm to derive. But in our case, and in most wallets that you see over here, you will always use 44 as the purpose. Third is the coin type. BIP44 was so futuristic, BIP32 was so futuristic that they said, yaar, ke kal ko aur blockchains aa jayenge. There might be Ethereum, there might be Solana. Of course, they did not know. But they said, we are going to create a generic method for any blockchain in the future. If you have Solana, then you can put 501 over here. As more and more blockchains start to get created, they end up taking one number over here. Ethereum, for example, has 60, Bitcoin has 0, and Solana has 501. So if you ever want to generate your first Solana seed phrase from it or Solana public private key pair from it, you will put 501 over here. If you ever want to generate Ethereum public private key pair from it, you will select 44 over here. That is what is happening over here, right? If you look at it, my account 1 has a Solana public key. It also has a Ethereum public key. It has a Polygon public key. It has a Bitcoin public key. This one uses the derivation path of probably M44 00. This one uses derivation path of Ethereum uses a derivation path of M44410 or whatever the Ethereum, this thing was, which was 60, sorry. And the Solana wallet over here, this one uses the derivation path of M4460. So, do we understand the significance of this third one? I think I went a little too fast here. But basically what is happening is, okay, given this root seed, I repeat, given this very big, random seed phrase that you have, not really random, it is derived from this mnemonic. You can generate Bitcoin addresses from it. You can generate ETH addresses from it. You can generate Sol addresses from it based on what derivation path you take. If you take M4460, M4400, I repeat, if you take M4400, then you're generating the first wallet on Bitcoin. If you take M445010, then you're generating the first wallet on Solana. If you take M44, what was the chain for Ethereum? 60, then you're generating the first wallet on Ethereum. If you take M4401, then you're generating the second wallet on Bitcoin. What is the second wallet on Bitcoin? This second account right here, the second Bitcoin wallet. So this is how a wallet like this generates various public private key pairs for you. It creates a mnemonic, generates a seed phrase. Given that seed phrase, it can derive various public private key pairs for you based on what derivation path you choose. I think I have the code for this somewhere as well. If you look at backpack configs solana/config.ts, it will show you various derivation path options. The one that backpack uses by default is this derivation path, that's M/44/ the name of the chain, which is 501 / this X here represents which wallet are you creating, wallet number 1, wallet number 2, wallet number 3, and then 0. This is the derivation path that backpack takes. But Solana has a legacy derivation path as well. People used to use this in the past. Now people are using this. In the future, some people might use something else. So it lets you choose between various derivation paths. For example, Ledger by default has this derivation path. Now what is Ledger? Don't worry about. Basically, Ledger is a physical device, and those people use this derivation path. So if you ever use a different wallet called Ledger, wahan pe your public private key pairs will be created using this. If you use Backpack, then your public private keys will be created using this. If you use Phantom, then it might be used by, it might use a different derivation path. This is why when Backpack was created for the first time, it first had to, give the users two options. Okay, are you coming from, Phantom? Then use this derivation path. If you are generating a fresh Backpack wallet, then use our derivation path. So even though this says, okay, derivation paths allow users to recreate the same set of addresses and private keys from the seed phrase across various wallets, that will only happen if these various wallets use similar derivation paths. If you create a third new wallet in the future to compete with these two guys, you need to make sure you use the same derivation path as they do. Otherwise, your user will try to come from here to your new wallet, and your user will not see the same set of public private keys. The user will be like, where are my funds? On Phantom, on Backpack, I see this public key. On your new wallet, why don't I see the same public key? So you need to make sure if you're creating a new wallet, you use the same derivation path that the folks at Phantom do or the folks at Backpack do. All right. Cool. This is the code that actually, can generate, let's say, 4 public private key pairs for you. Let's try this out using Phantom or Backpack. Let me generate a seed phrase in Backpack. Okay? Let me create a new wallet, select Solana. This is my seed phrase. Let me copy it. Let me go to Replit. Let me paste it. My mnemonic is not generate mnemonic, but it is this thing right here. All right. Let me click on next. Let me put a random. This time, let me make sure I'm putting the right thing. Next. A Backpack wallet was created for me. I repeat. I went through the full onboarding flow. I can see a single wallet was created for me. The public key of it is 6BAA is what it starts from. H7Q1 is what it ends from. Can I derive the same thing in my mini wallet that I'm creating here? I have copied the same seed phrase that came from Backpack. I've converted it into a seed. what code can I run so that I can get the same 4 derived wallets that I might get over here. Over here, if I create a new wallet, let me add a new wallet, and then let me add a third wallet, and then let me add a fourth wallet. I have 4 wallets over here. These are the public keys for it. Can I derive the same here? Given I have the same seed phrase, can I derive the 4 of them here? Let's see. Let's look at the imports here. What all am I using? I am using a few libraries here, and all of this code comes from Backpack only. If you go to Backpack and look at the code, you'll find something similar there. I use the NaCl library. I introduced this a while back. It lets you do cryptography. I use the ED25519 HD key library. This library, as the name suggests, on a ED25519 curve, lets you derive paths for a HD wallet, a hierarchical derivable wallet. And this key pair we've done many times, not many times, but once, comes from @solana/web3.js. These are the 3 set of things that I've imported. This is my mnemonic. I've converted it into a seed. I log the seed over here. I iterate from 0 to 4. And 4 times, what is my derivation path? M/44/501/I/0. Why is this my derivation path? Because Backpack uses the same derivation path. If I go to Backpack code base, what did you see over here? The derivation paths was an array, but if you look at the code, you will see it is the 0th derivation path that they use. M44501x/0, where x is the wallet index. The same derivation path I am using over here. I say the derived seed is again this derived path function that thankfully comes from here. What does it take as an input? It takes the derivation path, it takes the seed, converted into hex, dot key. This will give you the derived seed for it. It will give you this derived seed for the specific derivation path. From this derived seed, you can get the secret, from which you can create a key pair object on @solana/web3.js. So a few things are happening here. Let's go over them one by one. This is the derivation path. In every iteration, I will go up by 1. It will be 0, 1, 2, 3. The derived seed is basically, think of it like your private key only, but it's not in the right format, which is why we first use nacl.sign.keypair.from seed. Given this seed, can I get the key pair from it? I get the secret, and given this secret, I just convert it into the key pair format from @solana/web3.js. Even if you log this, that is fine. It means the same thing. But if you use this, then you will be able to get the base 58 conversion of the public key, which is what you see over here. In the Backpack wallet. If you look at Backpack, these are the 4 wallets I have. These are their base 54 encoded public keys. Do I get the same thing here? Let's see. 6BAA. What is the first public key in Backpack? 6BAA. What is the second one? 88U0. 88U0. What is the third one? 779Y. 779Y. 8YF8G. 8YFG. So, was I able to generate the same set of public keys here as Backpack? Yes. Can I create a wallet similar to Backpack? Yes, I can. Can other people who already have a Backpack wallet use my wallet over here? Use my simple web-based wallet that I've used? Yes. As long as they use the same, mnemonic over here, they can generate the same set of public keys like Backpack allows them, and Phantom allows them, and of course they can port over from Phantom to Backpack to Phantom, or Phantom to our mini wallet that we have over here. Now Backpack shows you a bunch of things. It doesn't just show you your public address. It shows you the balances that you have, how much of Sol do you have, how much of USDC that you have, what are your recent transactions that you did. Those are things we need to get to. We'll probably get to them this week. Okay, how can you actually query the blockchain for things about this specific address? Right now, we're able to derive the local address. We have not yet hit the blockchain. Phantom or Backpack do hit the blockchain. They find the balance of this public key and show you over here. That is something we need to do over here so that it actually becomes a wallet. Why do people install wallets? Because they want to see how much money they have. They want to send the money to somewhere else. We are doing the same thing here. We've reached step 1 of generating a mnemonic and, generating a bunch of public private key pairs from it. Again, this key pair is both a public and a private key. if I go over here, I have multiple public private key pairs now. And using these public private key pairs, I can have multiple wallets that are derivable from the same seed phrase. Given this mnemonic, I can convert it into a seed. Given this seed, I can derive a child seed. Given this child seed, I can get the public private key pair of that wallet. That is what HD wallets let you do. And that is a bare minimum of what you need if you ever want to create something like, or compete ever with Phantom or Backpack or MetaMask, because they will always all use HD wallets. They will not use simple key pairs. They don't expect their users to back up all public private keys. What was the problem that HD wallets fix? HD wallets are, this allows for generation of multiples from a single root seed problem. You have to maintain multiple public private keys. If you did what we were doing here, or what we were doing here, you would keep generating multiple public and private keys. And you would have to back all of them in your locker. You would have to write all those ugly looking private keys into your locker. Versus, if you do this, then all you have to back up is this seed phrase. From this mnemonic, you can get a seed phrase. From this seed phrase, you can get various public private keys. And always get this given the seed phrase. You can always derive multiple public private keys from these derivation paths given this root seed phrase. Cool. That is why you use HD wallets. And the assignment for this week was, okay, I've written some basic code that lets you drive multiple, Sol wallets. Can you drive multiple ETH wallets? Can you give the user something like this? Okay, this is your 0th Solana wallet. This is your 0th Ethereum wallet. And can you create a web-based wallet, which means can you, add UI on top of it, create a simple React application. A few people already did it. One person also got hired as a designer because his project was really good. So this is the one that Keshav created. If you click on generate wallet, it generates a seed phrase for you, something like this, a 12-word seed phrase. And then you can derive multiple wallets from it. Here is the first one. Can you generate more? I don't see a plus button here to generate more wallets. But you get the idea. Delete this wallet. Generate wallet. Oh, I guess I had to create generate wallet. Click on generate wallet. That's my bad. Current seed phrase, I can generate wallet number 1, wallet number 2, wallet number 3. Very similar to from a given seed phrase, you can have multiple wallets over here. So this was like a pretty clean project to build. He also built it fairly fast, which is why, he got in. But a few people are creating it. I was just looking at Twitter. Some other person also created it. This is what was expected from the assignment. And the next thing is, adding Ethereum support and letting the user actually hit the blockchain and, see their balances, then eventually maybe send transfers, so on and so forth. So that will be the next set of steps that we have to do to understand how can you now start to query the blockchain a little bit and, what is JSON RPC, which is what we'll discuss, in the next class. All right. With that, let's end it. I will see you guys in the next one. Bye-bye.